All right. Oh, I have some homework here for you. But I don't think there's going to be any questions about these homeworks that I'm giving back because just about everybody aced. Yeah. Aced it. So it's apparently pretty straightforward. Okay, but we do have homework due today. So do we have any questions about the homework due today?
Yes.
We do? All right. Which ones, now are you, what was it, the word, was it the word problems as opposed to the proofs?
No, I've got the proofs here. Don't disregard my quiz. Just disregard my quiz.
I just couldn't sleep.
Any questions?
Apparently not.
After a tall chai latte, Rochelle decided to go to sleep.
Any questions about the homework?
It's really hard.
For today, that's due today.
How many of them are actually valid?
How many of them are actually valid? There were 3 word problems, right?
Yeah.
And so how many of them are actually valid?
None. Because I'm pretty
One
sure.
was.
No, one was.
First one was.
I know one was because I used case analysis, but I was like, I'm not putting case analysis down because I did it in my head. I'm going to try to figure out how to actually solve it.
Yeah, remember I said that you're only allowed to use case analysis when I say prove by case analysis.
Well, you did. You said use 4.4 when you need to for 5.1.
What is 4.4?
4.4 is not case.
I don't think 4.4 is case analysis, is it?
4.4 is where you do proof by.
Assume the contract.
Yeah. Oh. Which I didn't use.
Yeah, 4.4 is by assume the conjuncts of antecedent. So that was a little hint. Okay, I'll give you a hint. One of them is not valid
Okay.
of the 3.
Stoked.
But are there no specific questions about these, about the homeworks? Because if not, we'll forge ahead. But I thought there were going to be questions. I was all ready to give you some hints, but
You want to give us the hints?
well, I was just going to. Was it okay getting them all set up? Were you able to get them all, translate from English to?
Yeah, now that I know that eventually it's the same.
Yeah, I'm just 5.1 ACB.
Wait, oh dang, I totally skipped D. But I'm not done with it anyway, so it's okay.
Oh yeah, I don't know where it was.
Okay, well, if there's no questions, then we'll
Can
go.
we prove 5.1c by just being like, I'm not a monkey? This is obviously. Wait, what?
5.1c.
It's like either there's a man on the moon.
5.1c is valid. Definitely.
Which ones did I ask you to do? A,
5.1, A, C, and D.
A, C, and D.
D
You.
is not valid.
Yeah, D I got not valid on.
Okay.
I got not valid on A, so.
No, that's valid.
That's valid? No, because C's valid.
No, yes, C's valid and A's valid.
Yeah, he said
And
1
then
is
D's.
not valid.
Okay, okay. never
What?
mind.
Okay, well, it sounds like there's no more specific questions, and the proofs were okay. I think the proofs are pretty straightforward.
I guess.
I mean.
The first one was.
Okay, well, let's go on. All right, now, we have one more assignment with word problems. And this next one is this problem has like a whole bunch of different parts to it, but it has a common intro. So this problem, exercise 5.6 from the book, is up on the screen here. And let's see, this first paragraph applies to all parts of the problem. So here's the setup. This set of questions concerns an island of knights and knaves. Knights always tell the truth, and knaves always lie. That's what makes them knaves. In formalizing these questions, associate identifiers as follows. Lowercase b stands for the phrase, big B is a knight. Lowercase c stands for the phrase, big C is a knight. And lowercase d stands for the phrase, uppercase D is a knight. Okay? Now, let me warn you that this next sentence is the key to setting up the Boolean expression that you can then analyze to determine what is true and what is false. The sentence says this: if B says a statement X, this gives rise to the expression B equivales X. Since if little b, then big B is a knight and tells the truth. And if not little b, big B is a knave and lies. Does that make sense?
Yeah, it's really cool.
Yeah, it's really quite clear. Clear as mud, huh? See, look. So, suppose B says. Suppose B says, quote, D is a knave. Suppose B says D is a knave, right? Well, suppose you have this sentence in your problem. Suppose, oh, sorry, not little b. Suppose big B says, because the inhabitants are the inhabitants are capital A, or sorry, capital B, capital C, and capital D. So B is an inhabitant of the island, right? Which means he's either a knight or a knave. So if B says D is a knave, how do you translate that according to this sentence?
It'll be.
Well,
B equivales.
B is saying something. So it would be B, what?
Equivales not.
Equivales,
Not D.
Not lower D.
not D.
Alright.
Now, the reason this is now do you see why
So say
this?
say
Because
it in English.
say this is true. Suppose lowercase b is true. But what this means is that these are the same, right? So suppose lowercase b is true. If lowercase b is true, then what do we know about big B?
Knight and he doesn't lie.
He is a knight and he doesn't lie. And therefore, he's telling the truth when he says that big D is a knave. And therefore, this is not D is true, right? So if he is a knight, then what he says is true, right? But if he is a knave, then what?
He's lying.
Then little b is what?
So,
Then little b is what?
knave.
If he is lying, then little b is what? Is false.
Right.
But in that case, what?
That's true.
That's
Yeah, this whole thing is false also. Which means that what?
D is
False equals
the D is true.
Yeah, we have false equals false. And this is still the case.
Sweet.
Are you with me?
Yeah.
So anytime it says, anytime an inhabitant says something, then that gives rise to this formulation. Okay? Now look, you guys, these A, B, and C, this is what you have for your homework assignment for Thursday, part of your homework assignment for Thursday. Someone asks B, are you a knight? He replies, if I am a knight, I'll eat my hat. Prove that B has to eat his hat. Okay?
How stupid these are.
Inhabitant, look at the next one. Inhabitant B says of inhabitant C, if C is a knight, then I am a knave. What are B and C? But these are all people on the island are saying things, and anytime they say something, that's whatever they say equivales whatever they say, and then that's true whether they are knights or knaves. And then you can do logic on this. How about the last one? It is rumored that gold is buried on the island. You ask B whether there is gold on the island. He replies, there is gold on the island if and only if I am a knight. Can it be determined whether B is a knight or a knave? Can it be determined whether there is gold on the island? But here again, he's saying something. Now, to give you to do an example, those are assigned, right? This one is not assigned. So I think what would be nice would be if we go through this question D, and we'll run through it to see how you manipulate these things with this concept of when an inhabitant says something, it gives rise to this expression. Okay? So, here we go. Are you ready? All right. So now what we have to do is we have to write down the relevant expressions. Now check this out. 3 inhabitants are standing together in the garden. A non-inhabitant passes by. That's like you. Okay, so you are a tourist, okay, on this island. And asks B, are you a knight or a knave? B answers, but so indistinctly that the stranger cannot understand. I am a... Okay.
He's a knave.
Okay. The stranger then asks C, what did B say? C replies, B said that he is a knight. But of course, C, you don't know whether C is a knight or a knave. But still, how can we translate C replies, B said that he is a knave? How can we translate that? C replies, so little c, yeah, good. So little c equivales is correct, but now what does it equivalve?
B equivales not B.
Yes, that's very good. How did you get that?
Because you have C says, so you have the C equivales.
C equivales.
And then he said B says
B says,
not B.
yeah, and B says, I'm not, or B says I'm a knave. So she said, he said. Are you with me? That's quite nice. Because it says C replies, okay? At this point, the third man, D, says, don't believe C. He is lying. All right. So now who's doing the talking? D is doing the talking. So that gives rise to what?
D says
D equivales, but now what?
C,
not C.
Not C. Yeah. Whew. All right. What are C and D? Hint only C and D statements are relevant to the problem. Also, D's remark that C is lying is equivalent to saying that C is a knave. So I think this is it. I think we got it. Okay. So let's work on this one. Now, do you see how we can do some now here again, it's kind of hard, right? Because we don't have something that we're trying to, I mean, we just have to start doing some manipulation. But I think, do we know enough about propositional calculus to where we can see right away how this one's going to fall out? What do we have? C equivales B equivales not B. So what is this?
False equals false.
How can we simplify this?
Contradiction. C
Well,
equals false.
I mean, isn't there something we can do here?
Yeah.
Doesn't this look familiar?
Yeah, it's like
Equals not B is
B,
false.
3.15.
B, what is
It's
3.15?
not P equals false.
So B equals not B must
False.
equival false, right? And that's 315, yeah?
Yeah.
315, C equivals false. Aha!
Oh,
So what do we know?
C is lying.
Now, if C is little c, what did little c mean? Little c means C is a knight. So therefore, what have we found out? So, big capital C is a knave. All right? But now what? Well,
O, D.
so now we have D equivals not C. So this equals by the fact that what?
that means D is telling the truth.
That C is false. C equivals false, right? From the previous conclusion, right? Are you with me?
We could just do that.
So this is D equivals not false. But what do we know about not false?
True. It is.
Well, is there a number for it?
313. Negation of false.
313, good.
Definition of false?
Yeah.
Negation of false.
So that's D equivals true. So what have we discovered?
D is a knave. No, D is a
So
knight,
D is a knight.
which means B is a knight.
Oh, wait a minute. But what about B?
The question is like asking for C and D. Can we find B?
Yeah, B's a knight.
I don't know if we can conclude that. Wait,
If
B?
B's a knave and C says that
What?
he said he's a knave.
Well, what B?
No. I don't think we can. I don't think we know.
Impossible because of what B said. Oh, but B lied.
Well, we don't know if he did.
Well, we don't know if he did or not.
But if B
So we know C and we know D, but I don't think we know what B is.
if B says I'm a knave, then
That's the most impossible statement.
he can't say that.
Yeah.
So you would have to be a knight.
Yeah.
B says.
If I say I'm a knave, then I would always have to be lying, which means I'm lying, which means I'm a
Yeah,
knight, but that's
no,
always
he's
still the
right.
truth.
He's right.
Oh, we can determine what B is?
Yeah.
Not through formal methods, it just makes sense.
If B says B is a knave, then either he's.
No, but C said, no. We don't know that B said that. We know that C said that he said
we know
that.
he had-
But we don't know if he, no. We don't know if he said that. No, hold it.
C's a knave, so he's lying, so therefore B didn't say that.
Yeah.
Well,
So
B
you
could
have
have
no
said
idea.
He
something
could have
else.
said anything. Even assuming he did say that, that is an impossible statement. Because can't say I am a knave, and
Yeah.
it'd be true if he's a knight.
Yeah, that is
I'm a
a,
knave, and if he's lying all the time, then that would make him a knight.
So the
which
only
is
thing he
not.
can say is I'm a knight.
Yeah.
Which
We'd
is-
have to assume that C knows that B is a knight.
well, no, he can say what, no, hold it. He can say whatever he wants.
B can't.
No,
B-
it's
it's-
that's a lie.
B cannot say that he is a
He
knight.
can't.
Look, okay, I can say, I am a knave. I can say that.
No.
I just said it.
If you're a knave, then
But-
you're
but you're
lying.
not-
I know, but that doesn't prevent me from saying it.
But you have to be on the island, and you have to be a knight, and only tell truth, or be a knave, and only tell false. It's the only impossible.
Oh, I see what you're saying.
So if you say I'm a knave,
Knave, yeah.
that's
Then you'd have to be
lying.
telling the truth if you were a knave.
And if you were a knight, same thing.
And
So
if you were a
that
knight,
would
then
violate,
you'd be lying,
that would violate the fact that everybody is,
They lie if they're a knave.
Everyone.
yeah, that would violate our original assumption that everybody is either a knight or a knave.
And in order.
But what are you if you say that?
Nothing.
You cannot say
You're a
that.
paradox.
You're a paradox. You're a paradox.
You're a
Yeah.
knight. Well, in
Yeah.
order for C to be lying, he'd have to know that B is a knight. So in order for C to be a knave, then he'd have to know that B is a knight.
Yeah.
So B has to be a knight. By informal methods.
By informal methods.
Methods.
Okay, now,
2010.
now look, you guys, whenever you do part A, whenever you set up part A, notice that he is saying, if I'm a knight, I'll eat my hat. So notice that what he's saying has a what in it?
Implies.
Implies. Yeah, so that's just a little thing to watch out
If
for.
only if it is-
If and only, yeah, good question. What is if and only if?
I feel
That's
like-
equivals.
I feel like he has to be a knave because he's wearing a hat. Not wearing a helmet.
Yeah, knights wear helmets.
Yeah.
Yeah, if he were a knight, he'd be wearing a helmet. No, that's not part of the problem statement.
That's the second axiom of informal methods. Knights wear helmets.
This is good. This is great fun, don't you think?
Ashley,
Yeah, totally.
say hi to her every day. What about Elizabeth? Say hi, Elizabeth.
They can't hear you.
Yeah, they
Yeah,
can.
they can.
Yeah, she always says, "Who said?"
Oh, really?
Did we pick up?
Or are you?
Hi, Karen.
Some people get picked up on the mic.
Okay.
People with
I get picked up.
people with volume.
You for sure they talk about you.
Great.
Okay.
Not all
Now the next thing we're going to do, we're going to skip now chapters 6 and 7
Why?
because they are not relevant for what we need to learn.
I like it.
It's some more. It's the theoretical foundations of logic, and we don't. It's like a big metatheorems kind of stuff.
So do we get to skip all that circuit stuff? Or is it really-
And we're going to skip the circuit stuff.
Is it stuff you can?
The circuit stuff. The circuit stuff in this chapter that we're going to skip. You're going to get a lot of that when if you take the computer organization course, and that's the one where we actually do circuits and you actually wire up little chips and stuff. No. Okay. So we're going to move on to chapter 8.
General laws of quantification.
Yeah. Now
This is like the one in the front, right?
We're doing quantum.
We did that.
okay, so the first thing that we're going to look at is our types. Now this table some basic types is on the front page of your handout. So you're going to have this on the next exam, as well as, so it's part of the packet, the usual packet. And so definition,
Is this chapter 8?
yes.
8.
Chapter 8.
A type, so we have to know what a type is. A type is a set of values. A type is a set of values. And this table shows us the types that we're going to be using throughout the remainder of the course. Okay, so we...
Only Booleans?
No, we're going to also do Booleans, but we're just going to add these additional types. Okay? Now, and for once in this book, these symbols for the different types are the symbols that are traditionally used in mathematics, in your mathematics notation. So this is, you can, if you use any of these symbols in your math class, your professor will know what you're talking about. So let's take a run through. So this Z, the way you draw this on your paper is you draw a big Z and then you just put an extra line here, okay? And so that big uppercase Z is the set of integers, and the integers are the numbers that can be either positive or negative, so they can have negative signs in front of them, right? So it's negative. It goes all the way from negative infinity, clear up to -3, -2, -1, 0, 1, 2, 3, clear on up to infinity. Okay, so those are the integers. All right. Now another one that we're going to use a lot is n. Again, it's drawn with this extra little stem or line through the middle stem here. And those are the natural numbers. The natural numbers are the counting numbers. So natural numbers are used to count things. Like you can either have, 5 sheep or 2 sheep or 1 sheep, or you might have no sheep. So 0 is a counting number, right? So those are the numbers 0, 1, 2, 3. Now that's in contrast to the positive integers. The positive integer is the same symbol for the integer, but with a little plus sign. Okay, so the z's are these z's, except restricted to the ones that are positive. And everybody knows, if I ask you the question, what about 0? Is 0 positive or negative? Trick question. What's the answer? It's neither. It's neither positive nor negative. Okay, so z plus are the positive integers 1, 2, 3, and then z minus, z with a minus, are the negative integers. And this other one are the natural numbers, q. So you do a q and you put 2 little lines here. These are rational. Okay. Now, so what is the definition of a rational number? Is the square root of 2 a rational number?
Yes.
Yep.
Are you sure? No.
It's not.
No, square root is rational.
Yeah, square root of 25 is rational.
Oh yeah.
Wait, what?
Okay.
Square root of 2 is not a rational number. How about pi? How about pi? Is pi rational?
No.
It's also not rational.
Really? Oh, yeah.
Because you can't, there's an approximation to pi. Did you know this? Have you heard of this approximation? 22 divided by 7?
Yeah.
Well, that's not exactly pi. Are you with me? What's pi? 3.1415962. And it goes on and on forever, and it never repeats. Right?
What does it mean by never repeats?
It never hits a pattern, and then that pattern is the same pattern, and then it's the same pattern.
Anywhere at all.
Look.
Even if it's a string of like 1,000 in a row,
It never repeats. Yes, that is correct.
Pi to 10 to the millionth power, and have yet to find any repeats.
You know what I think?
The next one repeats.
The next one.
Yeah. But if you write out 22 divided by 7, you do it. Somebody have a calculator?
No.
If you want to do 22
This
sevenths,
is math.
you'll find that eventually it will repeat. If it'll be 3.14 something something something, and pretty soon those digits will start to repeat. Now, why? Now,
It repeats after like 8 digits.
oh, do you have it there?
Yeah.
What do you have?
3.142.
3.142 what?
857.
857.
But
857.
Yeah.
142 857.
1428571 1428571, and it will keep repeating. But the reason that we're any rational, what does it mean for it to be rational? It can be written as I divided by j, for I and j being integers, as long as j is not 0, as long as you don't divide by 0. Are you with me? So this 22/7 is rational, but it's not equal to pi. It's just close. And this was a number that the ancient civilizations used. I forget which ones. Babylon, maybe. I'm not sure. Greece, maybe. They, but well, the Babylonians were before Greece, and they had some pretty high-powered math too. So anyway, so this one's rational. This one's not. So.
I don't understand why it's pie. Why do we call it pie?
Because it's delicious.
And then R, capital R. These are the R are the real numbers.
These are the pies.
Okay, these are the real numbers. So real numbers are numbers with fractions, like 5.783.
Just
You know.
anything, basically.
So the square root of 2 is a real number.
Yeah. Yes. Both the rationals and the irrationals are real.
So there's everything.
Isn't it everything?
Yeah.
They're
Well.
imaginaries.
Yeah, they're imaginary. We're not going to deal with imaginary numbers. Okay. And then R plus are the positive real numbers, and then the ones that we use all the time and will still continue to use are Booleans. So the Boolean type is this, and there's only two values in Boolean. There's only two Boolean values. So notice that all of these are sets of values. You know, a collection of values. Every single one of these is a collection of values. Now here's the thing.
What you do, everything else, you integrate from 0 to 0, and you add that, so you come back to what?
Here's the thing. Every expression E has a type T. Every expression
Think about it.
Really?
E has a type T.
So any expression that we come up with.
And it has a type. And what is an expression? If E is, it's either a constant or a variable.
We already did this on the test.
Okay, it's either a constant or a variable. If you use an expression in parentheses, if unary prefix, binary infix, right?
Yeah.
Every expression has a type. So now, expressions can be annotated with their types. Expressions can be annotated. What does it mean to annotate?
Shorthand,
Be lazy.
abbreviations.
No.
Means to write it.
Yeah, it means, yeah. Yeah, that's what it means.
Wait, these
Okay.
are really important. Pay attention.
Okay, so now look. So here's 1, right? Is 1 an expression?
Yeah.
Okay, so now I'm going to annotate this. The way you annotate it is you do 1. The way you annotate it is you put colon and then its type. So maybe I intend for 1 to be a what? What is this? An integer, right? So if I just write 1, it's not clear what this type is, right? This 1 could be a what? It could be an integer. It could be a natural number. It could be a positive.
A real rational.
It couldn't be a bool. So if I want to emphasize what its type is, we annotate it by putting a colon after it. All right? So here's another one. True.
I feel like we're getting into programming.
If we were it is a lot like programming. As a matter of fact, let me tell you this, a little fact here. Type theory is something that is distinctly a computer science way of dealing with these concepts. And in math, they're not so concerned with type theory. So type theory is very computer science specific. So how would you annotate this? True,
Colon B.
colon, Boolean, yeah, type Boolean. But now you see, what if you want to do this? What if you want to do 1 to the n? Well, you can annotate each one separately. Are you with me? So you could annotate this like this. You could say 1 type z raised to the n type what? Maybe you intend for this to be a natural number, right? So there's the expression, there is its annotation, right? And you could even do something like this. If you have x plus y times x, and you wanted to fully annotate this, well, how would you annotate the x? You could say x colon, maybe you want that to be a natural number, plus y, and maybe you want that to be a natural number.
Do we have to re-annotate x?
Yeah, and then you would do, well, you could, or if you wanted to. You don't have, I mean, these are optional. And then x, if we fully annotate it, would be of type n.
What if you want to annotate?
And then this whole expression is of type what? N.
What if you
So you could annotate it like that.
Second x not an n.
Yeah, if you wanted this second x to not be an n, then this whole expression would also probably not be n.
Wait, I mean, can you make one of the x's n and one of them not n?
Well, no, because it's the same variable.
Yeah.
All right. So this concept of annotation will come up occasionally. We will.
You can't multiply integers by booleans, right?
That's correct. You cannot multiply integers times booleans.
2 times true.
Why do we use Z for integers?
Why do we use z for integers? Do you know? I don't know why. Why?
It comes from the German word to count, which is zählen.
Ah, interesting factoid. Although I think it would probably be pronounced Zahlen, would it not?
Solid.
Zahlen. To count. From the German to count, and Z,
Stalin. That sounds like
it would be Z
Stalin.
also.
Quit Stalin.
Okay.
Peter Marx.
Now,
Maybe use Q.
now here comes something. All right. Now here comes something that is easy to forget. I don't know why this is always tricky, but functions also have types. All right? Functions have types. Now, what do functions return? I mean, when you have a function returns a type, but what else does a function have in parentheses? It has what? Parameters, right? And each one of those parameters has a type. Are you with me? So the question is, what is the type of a function? Well, the type of a function has to include the information not only about the type of the value that gets returned, but also the type, however many parameters there are, and what each one of their types is. So the type of a function has to include all of that. Now in computer language terminology, that's called the signature of a function. But we're not going to use that terminology here. So as a specific example, suppose we have a function of 3 variables. So suppose we have f of p1, comma, p2, comma, p3. Okay? Are you with me? So this is some function of 3 variables, right? Okay.
Sure.
Now, each one of these p's has a certain type. So let's say if p1 has type t1 and p2 has type t2 and p3 has type t3, and the function itself has type r, and f returns type r. Let's suppose that, are you with me? So maybe this is an integer, maybe this is a rational, maybe this is a real, something like that. Okay? And then this function does some computation, and whatever computation it does, it returns a certain type. Then, are you ready for this?
No.
Well, it's coming anyway. Then f, then f has type. Now, can anybody guess this, or does anybody know? I wonder if our cameraman even remembers this. What is the type of f? Is it?
Real.
No, it's not
You
just.
didn't write the real on it, right?
No, these could be whatever. T1, T2, this is in general, T1, T2, and if f has that, does anyone know, what is the type of the function?
Terminator.
F has the type, here, check this out. It is T1 cross T2 cross T3 arrow R.
What?
This is what the type of f is. The way you say the type of a function is however many parameters it has, they're on the left of the arrow. And it's the type of the first parameter, and this x is not times, this is cross product. Have you guys ever done cross product before with like matrices and stuff?
They're delicious.
Okay.
Is that arrow an implies or is
No, no, no. This is not a double-stemmed arrow. This is not implies. This is right arrow. Okay. So this is it's T1 cross T2 cross T3 arrow R. So if this function has 3 parameters and each one has type T1, T2, T3, and it returns type R, then it's T1 cross T2 cross T3 arrow R. And it's written like this. It's written F colon T1 cross T2 cross T3 arrow R. So you write the function name and then colon and then each parameter, the first parameter, the second parameter, the third, and however many, okay?
No matter what the parameters are, so if we have like,
If there were,
it's actually Z and then Z plus and Q, then you just have Z cross Z plus cross Q.
yeah, yeah. So let's do some examples. Now, as it turns out, a binary operator, think of it. What's an example of a binary operator? Say,
Plus.
yeah, plus, say A plus B. So, and what does plus stand for? That stands for like the sum of, so you could think of it as being the sum function with 2 parameters.
Okay.
Are you with me? So a binary operator is really a function of 2 variables. A binary operator is a function of 2 variables. And what about a unary operator?
A function with one variable.
A function of 1 variable. A unary operator is a function of 1 variable. Okay? So, here we go. Let's say that you have, so here's some examples. Let's say that you have the operator version. Okay? So with the operator version, you would say like 1 plus 3. Let's use your addition example. So you would say 1 plus 3, right? Now, if you were to write this as a function, then what would it be? If you were to write this 1 plus 3 as a function, what would you'd have this is the plus operator, right? So you would say plus parentheses 1 comma 3. Are you with me?
Yeah.
Now here's my question. What is the type of the function? Well, because when you're doing 1 plus 3, that's like having a function.
Why isn't it like addition?
Well, whatever you want to call it.
Sum.
Whatever, sum 1 comma 3.
Elephant.
Add 1 comma 3, whatever you want to call it. You can put whatever you want down there on your notes, okay? But my question is, if this is the function, then what is the type of the function? Let's suppose that we're dealing with in a program where these are all integers. If these are integers, if we're dealing with if this is integer addition in a program, then what is the type of this function?
Z cross Z arrow Z.
Yeah, very good. It's Z cross z, arrow, z. Is everybody with me on this? It's this is an integer, this is an integer, and when you add two integers together, you get an integer. So there's the integer, there's the integer. When you add them, you get an integer.
That makes way more sense than that.
Well, this is that. This is
I
that.
know, but that's.
Well, that's in general. So now how about look, how about this? How about this? Not true. Okay, so how would you write that as a function? How would you write that? Yeah, you would have a function like not, right? So you would say not,
True.
and we could, well, we have parentheses true. Remember that other notation? Dot true.
Not true.
Are you with me? Remember how with a function, if it has one variable, we use a dot?
Only one variable?
Yeah. If it's two, then you got the comma, so you got to put the parentheses. Okay. So not. But now, tell me, what is this? What is the type of the not function?
B arrow B.
Yeah. Is everybody clear on this?
R
Yep.
Because why? Because the argument is a Boolean and not true returns a Boolean. So the argument is a Boolean and it returns a Boolean. How about this? How about 5 is less than 3? If we wrote this as a function, what would we be doing? Yeah, let's call it less. Okay, let's call it the less function. And so we would say less 5, 3, right?
Yeah.
Now, you guys, what should the types of 5, what do you think if these integers, right? And there's two of them, z cross z, yeah. Z cross z, arrow, Boolean. Integer cross. Well, yeah, that's what. Is everybody clear on this? Does everybody see how this is just an example of that? And we could do lots of other examples, right? Are we good? Is this good? Okay. Now, the next symbol that we have to learn, which you might have run across before, it's a lowercase epsilon, Greek epsilon.
Do we set? Do we reassign operators?
No. Okay, so it's this symbol epsilon, right? Now here's the thing. Suppose that E is an expression. Big E is an expression. And T, lowercase t, is a type. All right? Then, if that's the case, then what happens is E, little epsilon t. Have you seen something like this before?
Probably on the front of our book.
On the front of the book, maybe?
We got B, epsilon,
Oh, you have that on the front cover of the book. Oh, nice observation.
D.
Nice. Oh, we're getting there. We're getting towards the front cover of the book. This means is an element of. And this whole expression is either true or false. It's a Boolean.
So E is a operator.
Well, this is a binary infix operator. This epsilon is a binary infix operator. And it's a symbol that means E is in this set of values. Because see, T is a set.
Type, which is a
Yeah, T is a type, which is a set. And it means E is in this set. So this is a Boolean, that means big E is in little t. So it's one of those collection of values, right? So tell me, what does this mean? Suppose we said let's do an example.
Is that imaginary now?
No. We're not doing imaginaries. suppose we say I is an element of n implies negative I is less than or equal to 0.
Like the elements first.
Well, what are the what are n? N are the what?
Oh, I being radical negative 1?
No. No.
That makes
I is not an imaginary. We're not doing imaginary numbers.
Make an X.
Okay, so what is capital? What is the n? What is the set n?
Counting number.
The natural numbers. Yeah, those are the natural numbers. So I is an element of the set of the natural numbers. I is in n. See, it means is in. So if I is in this set, what does that imply? Doesn't that imply that
It's,
that negative I
it's not equal to or less than 0.
is less than or equal to 0?
That's true.
So here's an example of the use of is an element of.
Wait, what?
It implies and follows from.
So now here's another example. If we have E and we annotate that with T, if E is of type T, then what do you know? What's another way to write this?
Then E-T.
Yeah, then E is an element of T. Is true. Evaluates to true.
But don't we assume it's true?
In other words, this and this really mean the same thing. Are you with me? Because what is the type? Because a type is a set. Okay?
I is just like a variable right there.
Yes, I is just a variable. Yeah, I is just, as lowercase letters are variables. Remember, uppercase, this uppercase is an expression. This lowercase is a variable. But yeah, this is a type.
But that whole thing is E. Is that what you said?
You can use upside down A.
If the expression E has type T, then E is an element of T. Evaluate is true because T is a set, and this means is in.
Two lines related at all?
No. Sorry, two completely different examples.
Can we
Sorry.
put another line on the T's to make it distinct? So it's not a variable?
It won't be necessary. It won't be. We will only annotate just occasionally. All right. Okay. Well, so we're just introducing some concepts here. We'll continue with this tomorrow. All right. So see you then.